Sorry, I'm okay.
Yeah, okay.
Okay.
So, welcome back, everyone. So, we are very happy to have Professor Daisuke Sagaki. I hope I'm pronouncing your name correctly. Uh, uh, and he'll be talking about Chevalley type formulas for level 0 Demazure models in terms of the quantum alcove model. Please.
Okay. Thank you very much for introduction and thank you very much for inviting me to this wonderful workshop. Okay, so today, I'd like to report a very new joint work with Kono and Leonard and Naito. So I got proof 2 weeks ago and I'm preparing preference. Okay, so let's start. Let's start with fixing some notation. Okay, hopefully these notation are standard for also for you. And let G be a finite dimensional simply algebra over the field of complex number C. And let GF be the affine, until affine the algebra associated to G. Okay, this one. And denoted by IF, the set of the index set for GF or the index set for the vertices for the linking diagram of GF, where I is the index set for G and 0 is the extended vertex. Okay. Okay, denoted by alpha I check. Denoted by alpha I check the simple correlates for GF, and denoted by alpha I the simple roots for GF. And delta denotes the null root for GF. Okay. Oh, so I should say, I should explain what she is. She is the central element in GF, and D is the degree operator. Okay. Okay. And then, so let W denotes the while group for G. This is finite while group, where Si is a simple reflection in the simple root alpha I. Let WF denote the affine while group for GF. Okay. Let denoted by UB of GF the quantum affine algebra over the field of rational function in B associated to this anti-affine real algebra. And denoted by EI and FI the Chevalley generators of the quantum affine algebra. Oh, so I use B here. Usually, quantum parameter is denoted by Q, but I will use Q in different meaning. So I use B here. Okay. So this is notation. Oh, this is still notation. So continue. Okay. So let H be the curtain subalgebra of G. Then the curtain subalgebra of GF is given by the direct sum of H and C and D. Okay? It is denoted by HF. Okay. Denoted by PF, the integral weight lattice for GF. Also denoted by P, the integral weight for G. Denoted by P plus, the set of dominant integral weights for G. Important remark is this is not for GR. Okay. So here in this talk, we regard an element mu, which is an element of H star. H is the curtain subalgebra G. H star is the dual space of H. We regard this element as an element of H of star by defining the pairing of mu and C, and mu and D is equal to 0. Okay, so this is remark. So an element lambda dominant integral weight for G regarded as an element of H of star is called a level 0 dominant integral weight for GR because of the pairing of because the pairing of lambda and C is equal to 0. So usually the pairing of lambda and C is called level, and because this pairing is 0 is equal to 0, so this lambda in P plus is called level 0 dominant integral weight for GR. So remark that this is not an ordinary dominant integral weight for GR because the pairing of lambda and alpha 0 check is negative integer in general. Okay, so this is our notation. This is notation in my talk. I think this is a very standard notation. Okay, let's go to the next slide. Okay, next I'm explaining what level 0 extremal weight modules are. Actually, yesterday Professor Lam explained what level 0 extremal weight modules are. So for those who attended in the Professor Lam's talk yesterday, this is just a review. Okay, this is just a review. Maybe my explanation is slightly different from his explanation, but my module in my talk is exactly the same with his talk. That is his module in his talk. Okay?
So there's there's a quick question from somebody in the audience, from Irfan Habib in the audience. Does the angular bracket denote the inner product for angular bracket of root systems?
No, this is just a pairing of H star and H. Okay, lambda is an element of H star, H star, the dual space of H, and C is an element of. Sorry, lambda is an element of H alpha star.
Yeah.
Okay, so and C is an element of H alpha. So we can naturally consider the pairing. So this is the value of lambda at T. Okay.
Yeah, yes.
Okay.
Thank you.
Yeah. Okay. First, let me explain what an integrable module are. What an integrable module is. In my talk, an integrable module over the quantum affine algebra is a module over quantum affine algebra satisfying the following condition. So this module M has a weight space decomposition with respect to the curtain part of UB of GR. Okay, like this. Okay, like this. By the way, can you see the pointer? Mouse pointer?
Yes. Yes.
Okay. 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 So M has a weight space decomposition like this. Okay. Second condition is important. The actions of the Chevalley generators EI and FI in the quantum affine algebra is locally nilpotent on M. Okay, this is the second condition. So usually, when we consider integral module, we assume that the dimension of weight space, the dimension of a weight space is finite dimensional. But in my talk, we don't assume that the dimension of weight space is finite dimensional. Okay, so weight space may be infinite dimensional. Actually, in fact, in general, weight space of level 0 extremal weight module is infinite dimensional. Also, the weight we don't assume that the weight system of M is bounded from above nor bottom. Okay? So the weight system of M could be like this. Okay. Okay, namely, so M is not an object of the BHG category O or O int in general. Okay, this is remark. Okay. Okay, next slide. Okay, definition. So let me define. Let me give the definition of an extremal weight vector. Let M be an integrable UBGF module. So let M be an integrable module over the quantum affine algebra. And so an element B of weight mu not equal to 0 is called an extremal weight vector of weight mu if there exists a family Bx indexed by the affine wide group of elements in M such that Be is equal to B and for X element of affine wide group and I an element of IR the following holds. So first condition is if n this is a pairing this is a pairing of x mu and alpha I check. If this n is greater than or equal to 0, then EIBX is equal to 0 and Fi to the nth Bx is equal to BSIX, where this guy Fi to the nth denotes the Q divided powers. Similarly, if this n is less than or equal to 0, then FIBX is equal to 0, and Fi to the minus nth times Bx is equal to BSIX. Okay, this is the definition. This is the definition of extremal weight vector of weight mu. Okay. So here is remark. So the element Bx, this Bx is an extremal weight vector. This Bx is also an extremal weight vector of weight x mu for x affine group element, affine wide group element. Okay. So this is a definition and remark for extremal weight vector. Okay. So this is a definition of extremal weight module. So due to Kashwara. So let lambda be an element. Let lambda be an integral weight. So remark that lambda is not necessarily dominant, nor not necessarily anti-dominant. Okay, this lambda is general integral weight. Okay, denoted by B lambda, the integrable UBGF module, integrable module over the quantum affine algebra, generated by single element B lambda, with the defining relation that B lambda is an extremal weight vector of weight lambda. So this is definition of B lambda, and we call this B lambda the extremal weight module of extremal weight lambda. Okay. So as I said before, so this explanation is slightly different from Professor Lam's explanation, but our modules are exactly the same. Okay. So here is the remark. So if the pairing of lambda and c is greater than 0, namely, so lambda is of positive level, then B lambda is isomorphic to an integrable highest weight module. Integrable highest weight module. Similarly, if the pairing of lambda and c is less than 0, namely the lambda is of negative level, then B lambda is isomorphic to an integrable lowest weight module. So we focus on the case that lambda is level 0, namely the pairing of lambda and c is equal to 0. So in addition, we have the following isomorphism. So So we have, just a minute, we have B of X lambda is isomorphic to B lambda for all X in WF. Okay, so we have this isomorphism. So we are especially interested in the case that lambda is level-0 dominant, namely lambda is P plus. Okay. In this case, we call B lambda the level-0 extremal weight module of extremal weight lambda. Okay. Okay, this is the definition of extremal weight module. Okay. Next, let me explain what level-0 opposite Demazure modules are. Okay, excuse me. Let lambda be an element of P plus, namely let lambda be a level-0 dominant integral weight. Okay. Recall that extremal weight module P lambda is generated by this P lambda is an integrable module over the quantum affine algebra generated by single element P lambda with the defining relation that P lambda is an extremal weight vector of weight lambda. Okay, so this is the definition. This is the definition. So by the definition of an extremal weight vector, there exists a family Bx indexed by affine Weyl group of elements in B lambda, such that Be is equal to P lambda, and satisfying these conditions. Okay, this is just a definition of extremal weight vector. Then, for an element x in the affine Weyl group, we define Bx minus of lambda by this formula. Namely, Bx minus lambda is UV minus of GF module generated by Bx, this Bx. Okay, this Bx. Because that this Bx is an extremal weight vector of weight x lambda. Okay, so this is a level-0 analog of the usual Demazure module. Okay. Okay. So remark that this Demazure module inside level-0 extremal weight module, not integrable highest weight module. So I should explain UB minus. So this is CB subalgebra generated by Fi. Okay, this is level-0 Demazure module. So recall that as I said before, so here, so as I said before, weight space of level-0 extremal weight module is infinite dimensional in general. So we can't define the ordinary character of level-0 extremal weight module because the weight space is infinite dimensional. But in this case, but for level-0 Demazure module, so we have the following. We have the weight space decomposition of this form. So Bx minus lambda is decomposed as Bx minus lambda nu, where nu runs over P plus delta, P plus Z delta, and each weight space is finite dimensional. Okay. So we can define character and graded character of B minus lambda. So we can define, this is character, this is just a character, this is character. So we can define this character. And also we put e to delta equal q. So this is called credit character. Okay. So when we set e to delta equal to q, this is called credit character. And this graded, we can see that this graded character is an element of this ring, where GP is the group ring, multiplicative group ring of P spanned by E nu as usual. Okay? So this is graded character. Okay, so let me explain what our Chevalley type formula is. So this is the main topic of this talk. So first, so let me explain our goal. Let X be an element of affine Wal group and let mu be an integral weight P. Integral weight. Okay. Let X be an element of affine Wal group and let mu be an integral weight. Then for every lambda dominant integral weight, such that lambda plus mu is also dominant integral weight, expand this graded character as follows. So this graded character, so expand this graded character as a linear combination of this graded character, where y runs over WR. So, so remark that this sum is possibly an infinite sum. So where Cy is an element of this ring, so same with this one, and is independent of lambda. So this is important point. This Cy is independent of lambda. Depends only on mu and x. So this is our goal. Okay. So we want to expand this graded character in this form. Okay. So let me explain the background of this problem. So actually, so there is a geometric background for this problem, but actually I'm very weak in geometry, so I can't explain enough. So I don't explain the detail in my talk today. So this is background. This is geometric background of this problem. Okay, let G be the simply connected simple algebraic group over C with H its maximal torus and G its real algebra. This is finite dimensional real algebra. So in this paper, in this joint paper with Kato and Naito, we introduced semi-infinite Frege manifold denoted by QZ. Also, we introduced semi-infinite Schubert variety associated to affine Wal group element, which is denoted by QG of Y. And so in this paper, we defined the 8 times C star equivalent K group of QZ, this QZ. In this K group, denoted by this symbol, the class of the line bundle associated to nu, and denoted by this symbol, the class of the structure sheaf of the Schubert, semi-infinite Schubert variety. Okay, so I don't explain what these are, but so what these are. So okay. Then if this formula holds, then so this product, okay, this is the structure, the class of structure sheaf of Schubert variety, and this is the class of the line bundle associated to minus W circle mu, whereas W circle is the longest element of W. So this product is expanded as the same way as this formula. Okay? So if we have an explicit formula for C-wise, then we have the explicit formula for this this formula. Okay. So this is the geometric background of this problem. So if you are interested in this geometric background, please check this paper or series of paper due to cutoff. Okay. So today we focus only on combinatorial aspect of this problem. Okay. Combinatorial aspect of this problem. Okay, let me introduce some known results. So in joint paper with Kato and Naito, we gave a Chevalley type formula for mu, dominant integral weight mu, in terms of the semi-infinite Lakshmi bisexual path of shape mu. Okay. So we want to, so in this slide, mu is an arbitrary integral weight. So, but this, so here, so this mu is integral weight, dominant integral weight. Okay, so we don't explain semi-infinite Lakshmi bisexual path. Okay. So dominant case is dominant case was done in this paper. Also, after this paper, joint work with Naito and Orr, we gave a Chevalley type formula for anti-dominant integral weight mu. This means mu is anti-dominant in terms of semi-infinite LS path of shape minus mu or quantum LS path of shape minus mu. Also, in this paper, we gave a Chevalley type formula for mu, dominant integral weight mu, in terms of quantum LS path of shape minus shape mu. Oh, sorry, this should be mu. So today I'd like to explain the Chevalley formula for arbitrary integral weight mu in terms of quantum alcove model introduced by Leonard Lobovsky. This is today's target, today's goal. Okay, so let me show you the formula first. Recall that affine Weyl group is decomposed as the semi-direct product of the finite Weyl group and translation parts. Okay, so where Q check is this span of simple chords for G, finite dimensional G. Okay, this is well-known result, I think. So main result of KNOS is like this. Let mu be an arbitrary integral weight, and let X be an arbitrary affine Y group element, and write it as W times T xi, W, where W is an element of the finite Y group, and xi is an element of Q check. Then for every lambda dominant integral weight such that lambda plus mu is also dominant integral weight, we have this formula. Okay? So we decompose this guy in as a linear combination of these guys. So here red symbols are symbols in red. For example, this guy and 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 this guy. These guys are those related to the quantum alcove model. And symbols in blue, this guy and this guy and this guy. Okay, and this and this. These are those related to multi-partitions. So in the latter half of my talk, I'm explaining what these are. Okay, here, so let's have short break for questions. Or, are there any questions so far?
So in the dominant and anti-dominant case, the coefficients are all positive, right? There's positivity. Is it true?
No. So in the case that in the case of anti-dominant integral weights, coefficient is negative. The negative means so Cy.
Well,
This
always,
coefficient,
always
so,
negative though.
No. Sometimes positive and sometimes negative. Alternating sign. Oh yeah, kind of alternating sign. So like this. So here's.
But in the dominant case, you have positivity.
Yes, I think so. Yeah, right. So this this minus one time to the something is disappears. Yeah, right.
Very good. Thank you.
Okay. Any other questions or comments? Okay, so can I go to the latter half of my talk?
Yes, please.
Okay. So in the as I said before, in the latter of my talk, I'm going to explain what these symbols are. First, let me explain those symbols related to multi-partitions. So first, this guy. This guy denotes the set of all multi-partitions chi equal chi I, such that chi I is a partition of length less than or equal to max of mu alpha I check and 0 for each I. Okay. This is a set of multi-partitions. Okay. Then, so so I have to explain this guy and this guy. So for an element chi, this is an element of this guy. With chi I is like this. Okay. So let chi be an element of this set. Then chi I is a partition of length less than or equal to this number. So we can write chi I like this. Then we set we define this symbol by the sum of all parts. Okay, all parts. So this is a non-negative integer.
Sorry, can I ask just so that I'm following? Yeah. So these multi-partitions are indexing the connected components of the crystal. Is that correct?
Yeah, but yes, in the case that rank mu is dominant, so this is parameter. This parameterizes maybe so. This parameter. I have to say so if okay, so this set almost parameterizes the connected component. Yeah, as you said. Yeah, right.
Okay. Thank
you. Yeah, if mu is dominant integral weight, so we consider power of mu without bar. So fit means so remove this or equal to. So less than.
I see. I understand. Thank you. That helps. Thank you.
Yeah, it's very related. It's very related to the connected component of crystal. Yeah, right. So also we define iota of chi by this formula. So namely the biggest. So this chi 1 I is the largest part of each chi I. Okay, this. Okay. So here also, if chi I is empty partition, we understand chi I1 is equal to 0. Okay. So this is this is a definition of this guy and this guy, this guy. Okay. So next, this is the main part of the latter half of my talk. So let me explain what quantum alcove model is. So this was introduced by Lennart and Lubowski. Okay, let H star R be the real home of H star spanned by alpha I. Alpha I is a simple root. So denoted by delta, the set of roots, denoted by delta plus, the set of positive roots. Also, for beta are roots, possibly negative, and sorry, this should be Z. So for beta and k, we define H beta k we define H beta k to be the hyperplane in HR star defined by this formula. Okay, here beta check is colored corresponding to beta. Then these hyperplanes H beta k, beta runs over delta and k runs over z, divide the real vector space HR star into open regions called alcoves, like this. This is A2 case. This is an example of A2 case. Okay, so this here is origin. Here is origin. Origin is here, and so this is pi 1 fundamental weight. This is pi 2 fundamental weight, and then simple root alpha 1 is here, and simple root alpha 2 is here, and each triangle is an alcove. Okay. So define alpha circle. This is not 0. This is circle. So define alpha circle by this formula. So and we call it the fundamental alcove. So in this picture, a circle is here. A circle is here. Okay. Also, we define an integral weight mu. We set a minus mu to be this alcove. So for example, so if alpha is if alpha is if mu is alpha 1, then if mu is minus alpha 1, then so this is a minus mu, because alpha 1 is minus mu. So and this is just translation. And so mu, so alpha mu is here. This minus mu is here. So and 0 is translated by this one. Okay, so this is a minus mu. Okay. And also we say that two alcoves are adjacent if they are distinct and have a common wall. For example, so this green alcove and this blue alcove are adjacent. Okay, because these have common wall here. Also, given a pair of adjacent alcoves A and B, we write like this. If the common wall is of the form H beta k, and the root beta points in direction from A to B. Okay, in this case, we can write theta. Theta is here. Theta is the highest root of A2. Or we can write minus theta. Okay. Okay, this is so this means this one. Then an alcove path is a sequence of alcoves A0, A1, am, such that aj minus 1 and aj are adjacent for every j. And then we say that an alcove path is reduced if it has minimal length among all alcove paths from A0 to am. Okay. Reduced alcove path and reduced. So this defines a reduced alcove path. Then let mu be an integral weight. Let gamma mu be an alcove path from a circle through a circle to a minus mu. Okay. Sorry, and this should be reduced. So we sometimes call such gamma mu mu chain. Okay, mu chain. For example, in this case, in this A2 case, if mu is minus alpha 1, then a minus mu is here. Then mu path mu chain is there are two mu chains here in this case. The one is this one, and then so arrows are like this. So here is this is theta, this is alpha 1, this is minus alpha 2, this is alpha 1. This is a mu chain. So there is another mu chain in this case. So namely, so here is, so and here is, and here is. So this is here. This is minus alpha 2, and this is alpha 1, and this is theta. Okay. In this case, there are two mu chains. Okay. Then, so let's go to next slide. So we want to define AW gamma mu. Okay, so this guy. We want to define this guy, AW gamma mu. Gamma mu is a mu chain like this. So in order to define this guy, we need the quantum Brillouin graph denoted by QBG of W. So let S beta be the reflection in beta for beta in beta denoted by S beta, the reflection in root beta. And the rho is the half sum of positive roots, okay, as usual. So quantum Brillouin graph is Q plus labeled, right? Q plus labeled directed graph defined as follows. The vertex set is given by W, Weyl group. And for elements B and W in W and beta are positive roots, we draw an arrow from B to W labeled by beta if the following satisfied. If the following is satisfied. Namely, so W is equal to B times S beta, and the length of W, this is length function. So length of W is equal to length of B plus 1, or length of W is equal to length of B minus 2 times pairing of 2 times the pairing of row and beta checks plus check plus 1. Okay. Okay. So under this setting, we can give the definition of AW gamma mu. Let gamma mu as above. This means gamma mu is a mu chain. So let W be an element of finite while group. Then a subset A, J1, J2, and Js, possibly empty, of the set of integer from 1 to n, 1 to m. This m is the length of this mu chain. And this subset is called the W admissible subset if there exists the following directed path in the quantum Fourier graph. So this direct path, namely W and W times S beta J1. There is a directed edge between W and W S beta J1, and then there exists a direct edge S W S beta J1 to W S beta J1, S beta J2, and so on. So here, this guy, this symbol, where we set sine beta to be plus minus 1, we define sine beta to be 1 if beta is a positive root. And then, so sine beta, we define sine beta to be minus 1 if beta is negative root. And then we define the absolute value of beta by this formula. Okay. So this is positive root. So also we define end of A by this element. Okay, this element. This is an element of finite while group. Okay. And we denote by we denote by A of W and gamma mu the set of all W admissible subsets of M. This symbol, this means this set. So this is a set of integers from 1 through n. Okay. Okay. This is a definition of this guy. So go back to our formula. So I have explained what this one is, and also we have explained what this one is. So I need to explain this one. Okay. So this one. Okay. Okay. So this is just complicated, but we don't use something difficult. So let's gamma mu. Because that gamma mu is like this. So this is a mu chain. This is a mu chain like this. Denoted by H beta J minus Lj, the common wall of Aj minus 1 and Aj, because that Aj minus 1 and Aj are adjacent. Okay. Using this integer, so Lj is integer. So using this integer, we define Lj tilde by this formula. Okay, this formula. Also, we define Rj hat to be S beta J minus Lj, which is the affine reflection with respect to this hyperplane, H beta J minus Lj. Then this is definitions for remaining guys. So for an element A of this form, for an element A of AW gamma mu of this form, we define NA to be the number of elements in J for which the corresponding root is negative root. Okay. And also we define weight of A by this formula, Also, we define M minus by this formula, namely, so this is a subset of A for which the corresponding edge in the quantum Fourier graph is a quantum edge. Namely, this satisfies Q. Q is here, satisfies Q. Okay. Then we define height of A and down A by this formula. Remark that J runs over A minus, this A minus. So I have completed the explanation of notation. So I want to show our formula again. So this is our formula. And as I said before, this formula has a geometric background. So as a corollary of this formula, we have this decomposition rule in the K group, our K group. Okay, so here are some examples. Assume that G is of type A2 and let mu be minus alpha 1. So as in this example. Okay, so G is A2, G is of A2, and mu is equal to minus alpha 1. So notice that this set of multi-partitions can be identified with non-negative integers. So in this case, this set is equal to the pair of chi1 and chi2, whose length is less than or equal to this number. But in this case, if I is this is 1, it should be. This is 1, this is 2. So if I is equal to 1, so this number is 0. So this number is equal to 0 because this pairing is equal to minus 2. So this number is equal to 0, and hence chi1 is always empty partition. Also, if I is equal to 2, then this number is equal to 1. Then we can regard chi2 as a non-negative integer. Okay, so like this, we can identify this set as a set of non-negative integer. So as I said in this slide, there are two mu chain in this case. Then setting W equal W0, W circle, this is longest element. So we compute these sets explicitly. So then, so for gamma 2, we have 12 elements like this, 12 elements. So each statistics are given as like this. Okay, like this. Then, so we have this formula. In this case. Also, whole gamma 1, so there are two mu chain. There are two mu chain. So gamma 2 is like this. Whole gamma 2 is like this. Whole gamma 1, there are probably 16 elements. Okay, there are 16 elements, but some cancellation happens in this case. For example, this green one and this green one canceled out, and this purple one is canceled out by this purple one. So what I mean is what I want to say is our formula, this formula is not cancellation free in general, unfortunately. Okay. Okay. Let me stop here. Thank you very much.
Okay, let's thank the speaker for a nice job. If you have any questions, please unmute and ask. Yes. No. Looks like there are no questions. Okay. Yeah, it looks like there are no questions. So let's thank the speaker and all the other speakers for this session.
Thank you very much.